Good day. My name is Oscar Daniel Madero, and I am currently enrolled in the Master of Engineering and Material Science program. The presentation will entail the exposition of a scholarly paper bearing the title Influence of Copper on the Mechanical and Dry Wear Resistance Properties of Titanium-25Nb16Hf Castings for Biomedical Applications. This work was developed under the direction of Dr. David Bravo Barcenas, a researcher at IXM City for Mexico, who was assigned to the University of Guadalajara. At first, titanium alloys are key materials in the biomedical field due to their high mechanical strength, excellent corrosion resistance, and biocompatibility, making them ideal for bone replacements such as orthopedic and dental implants. However, pure titanium has limitations, such as low fatigue limit and significant stress shielding, which can compromise long-term bone integration. Furthermore, wear resistance is a critical factor in bone implants, as wear regenerates particles that can induce inflammation and implant failure. This has led to the development of alloys containing elements such as niobium, hafnium, and copper to optimize both mechanical properties and tribological behavior. Niobium stabilizes the beta phase of titanium, which is body-centered cubic, reducing the elastic modulus and improving mechanical compatibility with bone, whilst hafnium adjusts the thermal and mechanical properties, although its effect on the beta phase is less pronounced. The beta phase provides ductility and fatigue resistance, in contrast to the alpha phase, which is hexagonal, close-packed, and offers greater mechanical strength. It has been demonstrated that copper modifies the microstructure at low concentrations. It dissolves into the matrix, but at concentrations above 5% by weight, it can induce the formation of titanium-copper intermetallic compounds, thereby increasing hardness and wear resistance, properties that are essential for minimizing particle generation in implants. The present study evaluates the wear resistance of the Titanium-25Nb16Hf with X-copper system, with copper additions from 0 to 7% by weight, a combination that has been little explored, synthesized by electric arc melting to ensure high purity and homogeneity. In order to analyze the microstructure and crystalline phases, X-ray diffraction and optical microscopy were used alongside Vickers and Knoop hardness tests, determination of Young's modulus, and tribological and surface roughness tests in accordance with established standards. The objective of this study is to establish a correlation between the microstructure influenced by copper and the wear resistance and mechanical properties of the alloy. This will enable an assessment to be made of the alloy's potential for use in bone replacement applications. As of materials and methods, the alloys were designed with a base composition of titanium, niobium, hafnium, copper, using powders of titanium, niobium, hafnium, and copper. In the formulation, the niobium content was maintained at a constant 25% by weight, while the hafnium content was set at 16% by weight. The copper content, on the other hand, exhibited a range between 0% and 7% by weight, with the remaining balance being attributed to titanium. The powders were weighed using a precision analytical balance and subsequently mixed to ensure homogeneity. Subsequently, the material was compressed in briquettes measuring 15 mm in a diameter, utilizing a stainless steel die. The briquettes were melted using an electric arc melting process in an inert argon atmosphere, with 3 remelting cycles carried out to ensure homogeneous composition and reduce segregation at 3000 degrees Celsius. This process yielded ingots of high purity and homogeneity. Following the acquisition of the ingots, they were subjected to a process of precise cutting utilizing a precision cutter and subsequently mounted in polymer resin. This procedure was undertaken in strict accordance with the guidelines stipulated within the standard ASTME 311, with the objective of ensuring optimal sample preparation. The mounted specimens were subjected to a sequential process of roughing and polishing. Structural and microstructural characterization was conducted utilizing X-ray diffraction and optical microscopy, respectively, employing standard procedures for the identification of crystalline phases and microstructural analysis. For the Vickers microhardness test, a load of 500 grams force was applied for 10 seconds, and the diagonals of the indentations were measured using an optical microscope to calculate the hardness in accordance with ASTME 9217. For the Knoop microhardness test, A load of 100 grams force was applied, and the anisotropy of the material in different directions was assessed in accordance with ASTM 38417. The aim was to determine Young's modulus from Knoop indentation measurements. This was achieved using a method developed by Marshall and Evans that relates Knoop hardness to the elastic modulus. This method is based on the relationship between elasticity and hardness derived from the geometry of the Knoop indentation mark. In addition, tribological wear resistance was assessed using linear reciprocating wear tests, in which the samples were subjected to a load of 2 newtons at the frequency of 2 Hz for a period of 3,600 seconds on a 5 mm track, using a 5 mm diameter aluminum ball as a sliding counter body. Once the test was completed, the coefficient of friction was determined and the wear marks were characterized using a three-dimensional profilometer, thereby enabling the volume of worn material to be quantified and the resulting surface topography to be analyzed in order to establish the specific wear rate. As illustrated in Figure 3, the X-ray diffraction patterns obtained for the analyzed alloys are presented. The absence of added copper results in the presence of alpha titanium and predominantly beta titanium phases. For the alloys containing copper at 1 to 7% by weight, the alloys predominantly exhibit the beta phase of titanium with a body-centered cubic structure, suggesting that copper dissolves in the titanium matrix, with it producing new phases detectable by X-ray diffraction, thereby completely establishing the beta titanium phase as the concentration of the copper addition increases. The images obtained by means of optical microscopy, as shown in Figure 4, provide information on phase formation, as reflected in the different microstructures observable in the various samples. A microstructural change is observed following the addition of copper, apparently caused by the stabilization of the beta titanium body-centered cubic phase at 1 to 7% by weight of copper, where quartz grains corresponding to the beta titanium phase are observed. In the samples devoid of copper, the alpha titanium hexagonal close-packed phase manifests itself and the microstructure becomes more intricate. This suggests that copper, at elevated concentrations, promotes a two-phase structure with the coexistence of the alpha and beta titanium phases. The microstructure of alpha-beta titanium alloys, such as titanium-6, aluminum-4, vanadium, is typically characterized by the presence of the primary alpha and beta phases. The alpha phase is typically basable as lamellar or acicular structures within a beta matrix. These observations are consistent with those reported for the sample devoid of copper. In the context of beta titanium alloys, which are subjects of extensive research in the field of biomedical applications, including titanium niobium and titanium molybdenum variants, the beta phase is predominant, resulting in a more uniform structure. This observation aligns with the findings reported for compositions exhibiting elevated copper content. In numerous studies on titanium niobium zirconium tantalum alloys, for instance, grain morphologies, analogies to those observed in this project have been documented. It has been demonstrated that the beta phase tends to dominate with an increase in elements that stabilize this phase, such as niobium or copper in this case. Consequently, the microstructures of the samples containing 1 to 7% by weight of copper show a reduction in the alpha phase regions, as reflected in the literature on the behavior of beta titanium alloys. As illustrated in Figure 5, the effect of varying concentrations of copper on the elastoplastic and tribological properties of the alloys under investigation is demonstrated. As demonstrated in Figure 5a, an increase in the copper content is indicative of a nonlinear response. The copper-free alloy demonstrated a hardness of approximately 295 Vickers hardness, followed by a gradual decrease to around 290 Vickers hardness for 1% copper and 275 to 280 Vickers hardness for 3% copper. Subsequently, the hardness increases slightly to approximately 282 Vickers hardness at 5% copper, finally reaching a value close to 365 Vickers hardness at 7% copper. This pronounced increase at a higher copper concentration indicates significant hardening of the material. This behavior has been shown to be associated with microstructural modifications induced by the incorporation of copper, such as changes in the distribution of alpha plus beta titanium phases, microstructural refinement, and solid solution hardening. Consequently, the findings suggest that the impact of copper and hardness does not strictly follow a proportional relationship with its concentration. Instead, there is a composition-dependent response, with the effect being particularly pronounced at 7% copper. Figure 5b presents a variation of Young's modulus, E, with respect to the concentration of copper. The reference alloy containing no copper has a modulus of approximately 82 gigapascals. When 1% copper is added, an increase to approximately 88 gigapascals is observed, indicating greater elastic stiffness of the material at this concentration. However, for higher concentrations, a downward trend is observed. The modulus remains close to 86 gigapascals for 3% copper, decreases to approximately 77 gigapascals at 5% copper, and reaches around 71 gigapascals for 7% copper. This behavior indicates that an increase in copper does not result in a continuous increase in stiffness. Rather, it modifies the elastic response in accordance with the composition, and possibly with changes in the structure and the phases present. The decline in modulus at elevated copper concentrations may be associated with alterations to the matrix, shifts in the proportion of crystalline phases, and increased microstructural heterogeneity of the beta-titanium phase. Consequentially, while minor additions of copper appear to result in a modest increase in stiffness, higher concentration seems to induce a decrease in the elastic modulus. Figure 5c illustrates the progression for the coefficient of friction over the course of approximately 3,600 seconds of tribological testing conducted under varying copper concentrations. It is evident from the data that all the curves show an initial increase in the coefficient of friction during the first few moments of the test, followed by a stabilization phase in which the values exhibit relatively small fluctuations. The sample devoid of copper demonstrates the lowest coefficient of friction for a significant portion of the initial test, sequentially attaining values approaching 0.60 to 0.65. In alloys containing 1, 3, and 5% copper, the coefficient of friction remains at slightly higher values, stabilizing at approximately between 0.65 and 0.70. The sample containing 7% copper exhibited distinctly different behavior, maintaining the lowest coefficient of friction throughout virtually the entire test, with values stabilizing at around 0.45 to 0.48. This reduction in the coefficient of friction for the highest copper concentration suggested an improvement in the tribological behavior of the surface. As illustrated in Figure 5d, the specific wear rate expressed in cubic millimeters per Newton meter is depicted as a function of the copper concentration. These results obtained demonstrate a distinctly non-monotonic trend. The copper-free alloy demonstrates a wear rate of approximately 1.3 times 10 to the power of negative 3 cubic millimeters per Newton meter. The incorporation of 1% copper results in a substantial enhancement of the value to approximately 1.7 times 10 to the power of negative 3 cubic millimeters per Newton meter, signifying a decline in wear resistance. Subsequently, at 3% copper, the rate decreases to around 1.4 times 10 to the power of negative 3 cubic millimeters per Newton meter, whilst at 5% copper it increases again, reaching approximately 1.9 times 10 to the power of negative 3 cubic millimeters per Newton meter. In conclusion, the incorporation of 7% copper leads to a significant decrease in the wear rate, reaching approximately 0.9 times 10 to the power of negative 3 cubic millimeters per Newton meter, which is the lowest recorded value in the entire series. This behavior suggests that the concentration of copper plays a significant role in wear resistance, although its effect is contingent on the composition. The significant decrease in the percentage of copper observed at 7% may be associated with the increasing hardness shown in Figure 5a and with the decrease in the coefficient of friction shown in Figure 5c. These conditions are hypothesized to favor a reduced loss of material during tribological contact. Figures 5e and 5f illustrate the three-dimensional images obtained by optical polyphotometry of the worn surfaces of the alloys containing 0 and 7% by weight of copper, respectively. Both images reveal a clearly defined longitudinal wear pattern accompanied by topographical variations represented by a color-coded height scale. The determination of the volume lost was based on the images obtained, with the objective being to establish specific wear rate values for each of the alloys. This study on the Ti25Nb16Hf with X-copper alloy demonstrates that the incorporation of 7% copper significantly optimizes its mechanical, tribological, and structural properties, making it an outstanding choice for biomedical applications, particularly in implants. A comprehensive investigation into microstructure hardness, Young's modulus, wear resistance, coefficient of friction, and specific wear rate of the alloy was conducted. The analysis revealed that the alloy containing 7% copper attains an optimal balance of properties in comparison with other concentrations that were evaluated. The microstructure of the copper-free alloy reveals a two-phase combination of the alpha phase, which has hexagonal closed-packed structure, and the beta phase, which has a body-centered cubic structure. However, the addition of copper results in the stabilization of the beta titanium phase and a reduction in the alpha titanium phase. The maximum addition of copper contributes to the marked increase in Vickers hardness to 356.64 Vickers hardness. Furthermore, Young's modulus is reduced to 70.76 gigapascals, a value closer to that of human bone at approximately 20 to 30 gigapascals, which reduces the stress shielding effect in implants, in line with research in biomedical alloys. From a tribological perspective, the alloy containing 7% copper is notable for its low specific wear rate of 0.9 times 10 to the power of -3 cubic millimeters per Newton meter, and the low coefficient of friction of 0.452, indicating excellent wear resistance and reduced heat generation due to friction. Thank you.